Welcome back to Space with SETI. Today we're going to be covering part 2 of my research on simulating the Milky Way, and if you're very confused as to what I'm talking about, click up here or one of the top corners for part 1. So let's quickly recap. The Milky Way is warped, and we think one of the main causes is the Sagittarius dwarf spheroidal galaxy, or Sagittarius for short. In my simulations, I model a Sagittarius-like impulsive interaction with the Milky Way and set up the sims so that the Milky Way is as close to the actual Milky Way as possible, but I vary Sagittarius's mass and see how the effects of mass change the warping within the disk. In my simulations, there is still even a warp even with the smallest Sagittarius mass, which is around about 10 billion solar masses. And in the highest mass simulation, which is 40 billion solar masses, the warping is extremely crazy and there's a lot of tidal streams and just general chaos. So now that we can see that the stars are moving up and above or below the disk plane and making all of these fancy corrugations, we can now use a model to try and fit the height and vertical velocity over time or over radius. If we look at, say, a very small ring of stars, we can see that roughly the one side is moving upwards and one side is moving downwards. This isn't always a perfect 50-50 split, but that is perfectly fine. Using this knowledge, I would suggest that we use a sine wave to model the height and the vertical velocity of the stars within these rings. So remember how I said that the fact that the vertical velocity and the height roughly look kind of similar in their patterns, it's just that the vertical velocity is shifted by about 90 degrees. Well, this is going to be important to inform us of what model we're going to choose. So we know that the derivative, or I guess the gradient of position, is equal to velocity. Well, we know that if we pick a sine wave to model our height, the derivative of sine is cosine, and cosine is just sine shifted by 90 degrees. Which is what we see in the height and vertical velocity based on the plots. This is a key indicator that a sine is probably a good pick to model the height and cosine for the vertical velocity. So I first up split the disk into little radial rings of a kiloparsec, each starting from 5 to 6 kiloparsecs, ending with 16 to 17 kiloparsecs. And for each of these rings I fit a sine wave, a model, which is sinusoidal in the form height equals a times sine multiplied by sine of phi minus the line of nodes plus some offset value z0, and I'll explain what these are right now. A is basically the amplitude, so this will be the peak value of the sine wave, so when sine is equal to 1, that's where it's at its maximum. Z0 is an offset which accounts for if the entire sine wave is shifted upwards or downwards. If you know Fourier decomposition, this is basically the unimodal term, and the sine wave, so the amplitude multiplied by the sine, is the bimodal term. Within the sine, we also have the line of nodes, and this is really important. It is where the this is where the warp hits the midplane. So that is where, as the stars are travelling through the warp, that is where they are at z equals 0. So what is the maximum height, if you will, of the stars for each radial ring? So that's going to be when sine is equal to 1, where it's at its peak, which is basically just the amplitude. We also want to add on the offset, and that will give us the height of the stars above the disk. This plot shows this. It's for all of these simulations together, but I've shown the outermost radii in the disk. When you go beyond this part of the disk, you have very few stars in each ring, so the fit isn't going to be as reliable. However, when you go further in towards the center of the galaxy, you have a lot of phase mixing, and so signatures are not going to be as well preserved. So the outermost bin is quite reliable in this case. I think this is really interesting. The amplitude after the impact is really huge, especially in the large simulation, and it's still quite sizable in the medium and small. But of course the control simulation looks so tiny and almost non-existent here. The decline is very similar in all the simulations, so everything is calming down within roughly the same timescales, and within about 2 billion years things kind of settle down, which is kind of what we could see in those videos that I showed in part 1. So now let's move on to plotting the line of nodes and see how that looks. it'll look extremely crazy if I plot it for all 4 simulations in one, so I'm only going to focus on the medium simulation from now on. In a perfect scenario, you should be able to use the line of nodes from both the position and the vertical velocity interchangeably. It shouldn't matter which one you want to use. That's not the case in the real Milky Way, and that wasn't completely the case in my simulations. So for now, I've just plotted the line of nodes for the position. You can see that in the green over here. And you can see that the general trend is that you do get some very big downwards dips, and that means the line of nodes is moving against the rotation of the stars, which means it's moving retrograde. But actually, the general, the most often case is that the line of nodes is moving with the direction of the stars, albeit very gradually, and this means that overall the warp seems to be moving prograde to the stars. So if we want to actually measure that precession, we can just calculate it by the gradient of this trend, so the changes in phi divided by the change in time. To do this, it's a little bit trickier than just getting the gradient of all of these data points. The problem is these data points are still quite noisy, and so if you just take such a small d phi value over such a small dt value, you can get a quite noisy precession, which doesn't really help to tell you much. So to do it for the purposes of this video, I fit a very smooth spline over the data points to try and reduce some of that wobbliness. And then I basically took the gradient of that and plotted that over here. Another thing I did was I fitted a very, very smooth polynomial, which should be kind of the same as the spline, but the polynomial is much smoother, and took the gradient of that just to show you kind of the rough trend that we can sort of see. So the polynomial is the super, super smooth curve over here in pink. And then what you can interestingly see with this precession is that you can see it kind of dips all the way down into the retrograde regime, and then it sort of climbs back up a little bit and then calms down to 0. And that kind of makes sense. The warping and the general craziness is kind of settling down, so it's very likely that you won't get a very strong precession. Now, I wouldn't take this plot too seriously. Fitting a smooth spline or a very smooth polynomial with few degrees is, it's a very quick and cheap way of getting it done for the purposes of just showing you the general trend. But yeah, I wouldn't take it too seriously right now as like really rigid data analysis. There is another way of estimating precession. This more focuses on using the continuity equations and sort of just looking more focused on the actual amplitudes as opposed to the line of nodes of both Z and VZ, and sort of comparing those to get an estimate for precession. This is a little bit more of an intensive method, and I'm currently still struggling with some of the data analysis, so part 3 probably won't be up until much later, but hopefully I can sort some things out. But yeah, I'll save that for another time, and I think we should just wrap it up now because that has been plenty enough maths and plots. But thank you very much for joining me today as I talk about my research. It was really fun, and yeah, I really enjoyed it, and I hope you learnt something new. I'll see you very soon in the next video, which probably won't be part 3, but will be focusing on something else. Remember to subscribe, and I'll see you very soon.